Hello, my name is Kirill Shmilovich, and for my poster submission to the 2020 AIChE Computational Molecular Science and Engineering Forum, I'll be briefly narrating my poster entitled Discovery of Self-Assembling Pi-Conjugated Peptides by Active Learning-Directed Coarse-Grained Molecular Simulation. In this work, we explore a class of molecules called pi-conjugated peptides that consist of a central pi core flanked by symmetric oligopeptide wings. This class of molecules has been computationally and experimentally demonstrated to assemble into pseudo-1D nanoaggregates where close proximity of neighboring pi cores results in pi electron delocalization and charge transfer along the length of what is effectively a biocompatible nanowire. The goal of this work is therefore to identify the combination of amino acids in the oligopeptide wing that best promote the assembly of these molecules into pseudo-1D nanoaggregates. We engage this problem using active learning directed molecular design, which is schematically illustrated here. In brief, the first step involves defining the forward problem, where given a molecular structure of interest, we perform a series of tests or experiments that allow us to evaluate the relative performance of that molecule. Step 2 involves explicitly defining the design space that we elect to work in. Importantly, framing the discrete molecular design space into a continuous low-dimensional representation that we can then directly expose to off-the-shelf optimization algorithms, namely Bayesian optimization in steps 3 and 4. We create this low-dimensional embedding by using a variational autoencoder, and throughout this work we use a previously parameterized bespoke coarse-grained model for pi-conjugated peptides, where the identity of each molecule in our design space is exposed to the variational autoencoder by defining its topology jointly using an adjacency matrix capturing the connectivity of the beads in the molecule, and a one-hot encoded composition vector capturing the identity of the different beads in the molecule. In the bottom right is a representative trajectory that's used to evaluate the performance of a given molecule, here identified by the amino acid abbreviations for the oligopeptide wing of the molecule, DDAI. And in the bottom is and the bottom shows the metric that we use to measure the relative performance of that molecule, namely measuring the average number of contacts per molecule in the simulation after 3,000 nanoseconds. Going on to the results, we see here a visualization of our three-dimensional latent space that we use for this model, colored according to the number of beads in the molecule, and we can see that the latent space smoothly captures these number of beads. We perform this optimization for a number of rounds, and after around 25 rounds, we are able to see convergence in the predicted performance of our model, suggesting the inclusion of more data will not significantly improve the predicted performance of our model, and also the posterior of our Gaussian process regression plateauing after a certain point. At the end, we were able to identify a number of promising chemistries that were previously unexplored by previous simulation or experimental works. Post-analysis of our trajectories using diffusion maps identified a number of kinetically meaningful coordinates that effectively discriminate between characteristically poor, intermediate, and good assembling molecules. And lastly, post-analysis of our trajectories further identified design rules for amino acids in the oligopeptide wings. For instance, the amino acids tryptophan and phenolphthalein were characteristically worse due to their large aromatic structures. On the other hand, amino acids such as aline, valine, isoleucine, leucine, and leucine were characteristically better as they are smaller hydrophobic residues that better promote hydrophobic packing. This work was recently published in a special machine learning and physical chemistry issue in the Journal of Physical Chemistry B, where it was awarded a Editor's Choice Award and selected for the front cover of the journal. Thank you everyone for listening.